Thank you, Ian. So before I start, I just wanted to say that in my early part of my career, I spent a year at the Institute, I guess on 3 separate occasions, and it was an extremely important part of my upbringing and my career. It's been many years since I've been back here for any period of time, and I wanted to thank Ian for setting it up so I could spend a few weeks here and so to give this talk. What I had in mind today is actually to give a bit of a survey talk about certain types of geometric structures and a process involving deforming them and so on. And the theme I want to sort of beginning point is that when we think of geometric structures on 3 manifolds, in particular Thurston structures, we tend to think of them as coming in little clumps, right? They're manifolds that have spherical structures, one that have Euclidean structures, some of the various fibered structures, and then most of them have hyperbolic structures. But it turns out that if one allows a certain amount of singularities in the structures, that there's actually a lot more close connection between the various geometric structures, and that's sort of, so we'll see, that's a sort of transition part of the talk here. So I think somehow one can't really talk about this without starting at sort of canonical starting point. In particular, I'm going to let M3 just be the 3-sphere minus figure 8 knot. So again, standard sort of picture here. So the complement of this has what? One extra crossing. Okay, well, okay. 1, 2, 3, 4. Okay, right. Has a, in fact, a unique complete hyperbolic structure. By Mostow-Prasad rigidity. However, if one allows to take incomplete structures, there's in fact a large family of these, and this is the whole beginning of Thurston's idea of hyperbolic Dane filling, Dane surgery, ways of getting hyperbolic structures on Dane filled manifolds coming from knot complements and other finite volume complete structures. So in particular, we can consider incomplete structures. And then when we complete them, the completion we want to assume is what's called a cone manifold. So this is a structure, this will actually be a singular structure, actually hyperbolic structure on the 3-sphere here. In particular, if I look at a neighborhood of filling this in, but allowing a singularity along the knot here, then the local structure here as I go along like this, along here, with this as the piece of the knot. Then if I take a cross section, there's a singular point, and it has cone angle, in our case, less than 2 pi here. And this can be thought of as obtained from a piece of hyperbolic space where I have angle here and have a singular point there. Okay. So you can deform the complete structure, which you think of having cone angle 0, through some small cone angles. And in particular, in this particular example, work of Hilden, Lozano, and Montesinos, showed that for angles, including the complete structure here, up to 2 pi over 3, we actually have hyperbolic structures. At cone angle 2 pi over 3, there's actually a singular Euclidean structure. It's actually an orbifold structure. And then at least for, say, 2 pi over 3 actually goes a little further, but up to, say, cone angle pi, there actually are singular spherical structures. So some of you know if you take the two-fold branch cover of a two-bridge knot like this, you get a lens space, and that's dividing out by order 2 thing here. You get the spherical structure with cone angle pi here.
The exact upper.
Pardon?
Is the furthest upper?
No, you can go further, but anyway, I thought.
Is that an unknown? What happens?
Yeah, people know what happens, but but it's a little more complicated. But at any rate, that's not really the. But they actually explored this a little bit more, in their paper. Yeah. So in particular here we have, if you take on the complement here, this gives the holonomy representations from pi 1 of M3 to SO31. I'm going to think of hyperbolic isometries that way. Down here it goes pi 1 M3 to SO4. And then down here we have, I'm going to put a little tilde on this, you'll see why in a second, M3 to isometries of Euclidean space. So what actually happens is for the non-zero rho t's, as t goes to 0, these actually, as representations converge to representations that go, in fact, to SO3, which are actually subgroups of, or correspond to the isotropy subgroup of a point of in each of these things here. So what's actually happening for both the hyperbolic and the spherical structures is they're actually collapsing down to a point. And then the holonomy actually just is something that fixes a point here. On the other hand, you can probably remember we have isometries of E3 goes down to SO3 with R2, R3 sitting in here. And what we actually are seeing here is pi 1 of M3. The limiting representation of these rho t's goes into here, but you can actually lift this to something that actually goes into the isometries here. And in fact, there exists a smooth family of rho t tilde going from pi 1 of M3 into PGL4R, which we can think of PGL4R. All of these groups here can be thought of as living in here. And in fact, then, let's see, these guys, these are all conjugate to rho t in this thing here. So basically by doing a projective, so this is a projective group, projective transformation, you can keep these things from collapsing in terms of the representation and actually get a smooth family that passes through the isometries of Euclidean space. Okay. So this is sort of the simplest kind of degeneration where everything kind of collapses uniformly to a point. The thing I'm going to spend most of my time talking about is when instead the hyperbolic structures collapse down to a two-dimensional representation. That turns out to be a lot more complicated and a lot more different types of things actually happen. So I guess, if you like, I'm going to basically, this talk will consist of 4 examples, or types of examples. That was the first one. Second one here comes from if I take a surface, closed orientable surface, genus G, greater or equal to 2. Let's see if I can do this in an organized way. And I want to consider representation of this into the two-dimensional. So take a Fuchsian representation here, sitting inside of the three-dimensional hyperbolic isometries here. So these are Fuchsian representations. So maybe if I call this rho, I guess this will be rho naught ultimately. So in particular, there's a whole large space of these called the Teichmuller space. I'll just denote by this, which is a large 6G minus 6-dimensional ball. So when I take hyperbolic 3 space, thinking of this as sitting in isometries of hyperbolic 3 space, we end up with, if you like, H3 divided out by gamma. It looks like this. It's infinite volume. It has a totally geodesic subsurface sitting in here, coming from the image of the hyperbolic two-dimensional hyperbolic space that's preserved by this here. So this is totally geodesic. But then I can deform this within three-dimensional hyperbolic geometry. And again, I get something that topologically, at its infinite volume, topologically, it still is a surface cross R, but it no longer has this totally geodesic surface sitting inside of it. It has a kind of wiggly surface, I guess. Nothing canonical here. And as I say, this still has finite infinite volume, but by taking what's called the convex core of this structure here, you can actually get something with finite volume. So it has the following structure. Never really learned how to draw this properly. So it's a totally geodesic, so the boundary of the convex core is totally geodesic surface. But as I've tried to draw here, bent along a geodesic lamination, a measured geodesic lamination. So if you're not familiar with geodesic laminations, you can just think of simple closed curve. So there's one on the top, I'll denote that by mu, and one on the bottom, lambda. And I'm not going to attempt to draw it like it's bent, but at any rate, there's some curves here that which is bent here. Okay, so we think of this as what I call it, lambda here and mu here. So it's natural to ask which laminations actually appear, or pairs of laminations appear in this form. And there's some obvious necessary conditions. Are that the pair mu lambda are in what are called filling measured laminations. So there are two properties. One is that if I take the union of these thought of as on the same surface, they fill the surface. I'll explain what that means in a minute. F2. And then another condition here, if indeed this is not a full lamination but is a closed curve, the amount, so there's a measure, the reason there's a measure here is because it picks up the amount that it's actually bent. Okay, so the larger the measure, the more it's bent. When it's a simple closed curve, you can think of the amount that it's bent as an angle, and then here the particular that if either mu or lambda are, this is a simple closed curve, or even a collection of them. If it's in there, then the weight is strictly less than pi. You can't bend more than pi, or even up to pi. So these are necessary conditions, and then it's a very nice theorem of Bonahont and et al. That oh, sorry, I meant to say, so what does it mean to fill? If it's a pair of simple closed curves, it just means that every simple closed curve on the surface intersects at least one of them. If it's a geodesic lamination, it's a similar sort of statement that if you take the union of them, then the complementary region is a collection of, in fact, compact polygons. Okay, so it just there's no room for a simple closed curve or anything in there. And it's not too hard to see that these are necessary, because if there were, since this is supposed to be a convex core here, if there were room to stick a simple closed curve in the union here, these guys would actually be flattened out completely like that. So that's the reason it's sort of clearly necessary. But they prove that, in fact, it's sufficient every realized, and in fact, if mu and lambda are both weighted collections of simple closed curves, there's a unique quasi-Fuchsian group that realizes them uniquely. It's still unknown whether this uniqueness holds in general. So the uniqueness here actually corresponds to comes from work of Craig Hodgson and myself, the local rigidity, which I think probably should be spelled rigity according to the way my title came up, which was completely my fault. But at any rate, just to show I do know how to spell it. Actually, using that and some of their deformation theory, I can prove that, in fact, they're sort of uniquely here. OK, so we have lambda and mu, and with these provisos here, you can realize any pair with these conditions. But now I want to consider, well, let's fix mu and lambda, realized one in here. And now I want to start with something here and now just start decreasing the weights. Okay, flatten it out. And then consider. So I'm just going to change the measures, which you want to think of. So again, this condition, since and then where A and B are going to go to 0, and I'm going to have them go to 0 in a uniform way. I'll say in a second. Yeah, it comes from doubling and so on, but I'm going to do that in a second on the next board. Yeah. Right, so consider this. So in this situation, we have, so then we have, if you like, we have a family. Just think of A and B going in a linear fashion in this way towards 0. We have, therefore, a one-parameter family of representations of the surface group into SO31. But then this converges to something in here, which is actually Fuchsian. Because it's completely flattened out, we're back in this picture with a totally geodesic thing. On the other hand, particular, say if we're in the simple closed curve thing, all along the way there is a unique structure with weighted bending on the simple closed curves. But then in the end, we hit some Fuchsian group that actually has a huge amount of flexibility, right? So this was the sort of thing that my rigidity and flexibility thing was about. So the question is, we can ask which one does it actually converge to? It only converges to, well, first of all, saying that it converges, but in fact, what does it converge to? So this was answered by Bonahan, and with some further refinements by Caroline Series. So these are separate separate papers. They showed that the rho naught corresponds to the hyperbolic surface, right? Because it's a Fuchsian group, with the property which is where the unique minimum. So geodesic laminations have a notion of length. Just again, hyperbolic length. If we're on a hyperbolic surface here, if you like, just continue to think of simple closed curve, and then if you weight it, you multiply it by the weight, where the unique minimum. So in particular, you can consider the length of actually. So actually weighted. So you can take the length of mu, weighted by some positive number x, plus the length of lambda, weighted by y. So this is now a function from Teichmuller space to the positive reals here. And again, we want x and y positive, such that x over y is the same, is equal to c over here. So the fact that something like this, where the two laminations fill up and you take any, so if you think of this as a convex combination, has a unique minimum, corresponds to certain convexity properties of length functions on Teichmuller space. So in fact, there is a unique thing picked up by the things that are bent and then the ratio at which they are bent that tells you which point you're going to hit in the Teichmuller. So in particular, by varying, so in particular I have this big, I'm just going to draw it as a disk, but a big Teichmuller space here. And what it says is that on here, there's a single point that we come down as we flatten out in this way that it collapses to here. And in particular, as I vary x and y, we actually get a line, kind of line that behaves vaguely like a geodesic and hyperbolic geometry. This is called a line of minima. So this is where I vary the ratio of x and y here.
Could you say, is it possible to use the data of mu, lambda, and c to predict the systole of the unique minimum?
Not really. I mean, predict at some level, but yeah, it's hard to say exactly what the geometry of the minimizer is going to look like.
Can you say how its short curves intersect mu and lambda in some sense?
Well, they can't be too short because it's taking place in a compact. These will sort of be in a compact region. So okay, but the point here is that if you think instead of starting with the Fuchsian group and regenerating or pushing it into a quasi-Fuchsian group in such a way that it's bent along lambda and mu, it says there are only very few geometric hyperbolic surfaces for which this is possible. And in fact, if you decree on what the ratio is, there's in fact a unique one. Now, in the special case, when mu and lambda are simple closed curves, weighted simple closed curves here, then in fact we can double the structure here very easily and get a nice, so this will go back and connect with our cone manifold structure that we talked about over here. So then we can double the convex core. And then what we end up with is we get a cone manifold structure. So when you double, this is just, if you ignore the bending, it's just a surface cross an interval. When you double it, you get a surface cross a circle cone structure on F2 cross S1, but where the singularities are on, so maybe I'll call these, U and lambda here, where the singularities lie along these simple closed curves. So we get the following picture of where then this is identified to this just by the identity. And then I have, say, mu sitting up here and lambda sitting down here with singular structures here, and in particular as going back to this picture as AB goes to 0. So we have a singular hyperbolic structure, then this flattens, this collapses to an H2 structure. And in fact, we know which one, the one I just talked about over here. Because these cone angles around here are just twice the amount of bending that I have over there. Okay. So there's a reasonable, I mean, there's a singular but robust hyperbolic structure on this when there's bending, but when it flattens out, the whole thing, what we would have, we couldn't have a hyperbolic structure because that would be a hyperbolic structure on a surface cross S1. All right. On the other hand, when you have the surface cross S1, there in fact is a projection. So in fact, it collapses in a fairly controlled way. You actually have so that have a one-dimensional foliation just corresponding to the circles, but with a transverse hyperbolic structure. And this is typically what happens when you have a manifold like this with cone manifold that collapses down to a two-dimensional hyperbolic structure or hyperbolic representation, that when you see when it collapses nicely, you actually get some extra structure. You get some kind of one-dimensional foliation with where the fibers from the projection down onto the collapsed structure actually have this nice transverse structure. So in answer to Dave's question here, so for these sorts of things where the cone angles, so hyperbolic cone manifolds where the cone angles are less than or equal to 2 pi, so the local rigidity results that Craig and I proved say that the structure is locally rigid rel the cone angles here. Okay, so that's the result. So to turn that into a global thing, you need to be able to, say, decrease the cone angles all the way back to, say, where the cone angles are 0. Then you have a complete hyperbolic structure which is rigid. If there had been any non-uniqueness, it would have to have branched at some point. So it's a sort of standard thing. But you do need to know that you can push all the way back to where these cone angles are 0, and that's part of what comes out of the Bonahal et al. Okay, so it turns out that, actually let me write it over here. There is in fact Schlenker really working from stuff from Jeff Mess's work, said there are in fact ADS, meaning anti-de Sitter analogs of quasi-Fuchsian groups. And again, they have a convex core, that are bent along hyperbolic laminations in the same way. And what he proved was something not quite as strong as the Bonahon et al., but in particular he generalized or gave an analog version of the Bonahon series results. So what's the isometry group? So we had over here, so again, let's think about in this context here, we have a bunch of representations here from pi 1 of F2 cross S1 minus, so this is now, I'm going to call this a singular set here, into SO31. It collapsed down to something that went into SO21. The isometry group for ADS is up to index 2 things. Again, from here, SO22. So you can again see the same sort of situation we had here, where you go from SO31, pass through something that, well, goes down to SO3, but then goes into SO4. So here you see a similar thing, SO31 collapsing to SO21, but also from two directions, from this direction and this direction. I didn't organize my boards quite so well, but anyway, let me just say that there is a, so I'm running a little short on time, there's actually an analog of, so this is sort of like the SO3 over here, there's an analog of isometries of E3, so, so the analog of E3, in this case, a thing that is kind of the lift of this, E3 isometries, is equal to what's called HP, or half-pipe geometry. So this was developed by Jeff Danziger. Let me just say that the in PGL4, the matrices look like they have a copy of SO21 up here, a 1 there, and then some vector here that corresponds here. So any rate, again, by conjugating everything in PGL4, you can actually find a smooth path through here. Okay. So actually that's something that Jeff and I worked out together in this particular example. Okay, third example. So again, I'm concentrating less on the transitions here and more on the question of the kind of unique structure that you collapse down on here. Here it was the sort of unique minimum of, mine's turned off, isn't it? Yeah. If you have questions, you don't have to call in. Okay, so so the next example.
So could I ask?
Yeah.
Possibly go the other way. So you're saying if given mu and lambda, then you can kind of figure out which function you're going to land on. What if you have rho naught and lambda? Can you predict what mu will be? Is there
Yeah, it's the unique, I mean, right, that's a theorem. It's also true that given lambda and a surface, there is a unique kind of perpendicular or whatever lambda. Yeah, it's perpendicular in a suitable sense. It's kind of the analog of the Hubbard-Maser theorem for for measured foliation. I was part of my stuff when I did the lines of minima. But it comes from earthquakes and so on. Yeah. So this time, so for this thing here, this is going to be an orbifold, closed orbifold. And in particular, it's going to be Seifert fibered. So as you know, a Seifert fiber manifold has a property, it's foliated by circles. And it's sort of a generalized circle bundle, but locally you don't necessarily have a product structure, but instead you have, at certain isolated fibers, you have a cylinder with vertical fibers, but then you have a rational twist of some sort. So this is just a orbifold version of that same idea here. And in particular, with a Seifert fiber orbifold, there's a notion of a base where you quotient out by the fibers. And so here we want the base to be equal to P, which is going to be a hyperbolic polygon. So if you like, we might have the polygon P be something like this. And then you want to think in terms of the hyperbolic structure of like the reflection group in this thing here. So we have like reflections on here, and then the stabilizer, well, and then here we have some angle of the form pi over alpha, where these are integers, etc. Okay, so that's what the base looks like. And then, so in this case, the fibers are of two types. They're either equal to S1, or you can also have an interval fiber where this really means the orbifold where you have twos at here. So this is just what I get by taking the circle and reflecting on it. So, okay. So these are the fibers that I have over here. So in this fibration, what do I have over a regular point in the middle here? So the fiber over sort of a regular point here, right, is just a regular fiber, the usual picture, just a circle bundle picture here, where this is just sort of by the identity over here. Say maybe that's the going down here. Okay, the fiber over the edges is going to be an interval. And then the local neighborhood looks like this. So for a point here, and if you like, there's like a whole sort of edge that this pushes down to over here. And if I take an interval here, again, just with the product foliation on this cylinder, and I just fold, in a way, fold the top and the bottom. So you can see that if I'm off of the red line, I go up here and then down there and over there. It's just a regular smooth fiber. Whereas if I'm on, let's see, make this maybe an X over a point here, then the point here like this, then in fact there's a whole kind of interval's worth of I fibers. And then finally, over the vertices, it's a similar picture, but these two lines are now rotated to each other at some rational angle, rational multiple of pi. So over here. And so in particular, what am I left with? Say a square there. So over a vertex here, the square there. Then what you see, again, it's an I fiber, But notice that if I take any other point, say nearby here, it goes up here and then wanders around for a while and then eventually closes up. So it's still an I fiber, but it's longer, just in the usual Seifert fibered sense. Okay. So these are like the singular fibers, so this is where the singular fibers come from. So here's a concrete example. This is why I've been struggling not to. So this is a Montesinos link. And then the link itself, the so-called sort of horizontal pieces here, they all have 2s on them, so they project down onto the edges. And then there's you throw in a singular. Doesn't really matter where you put it, but what color was it? Maybe red or something here. At each of these, you throw in something that goes like that. So here the singular locus is actually a graph. And in fact, in these cases, the complement of the singular locus is actually a handle body. So instead of having a boundary equal to a torus, which we've had in the past here, we actually have a somewhat more complicated boundary when you take a tubular neighborhood of the singular locus. Okay. So this is a good typical example to think about over here. So. That corresponds to the fibers over the. Oh, no, that was only red. Okay, at any rate, fibers over these guys here. So that's like this sort of, yeah, I guess color coding. That should have been red over there. Okay.
The vertical.
Yeah, right. So thank you. Actually, the terminology here is these singularities along here. This is called the horizontal part of the singular locus, and these are called vertical parts. Okay. Okay. What?
And all of it should be red in the Montesinos.
Okay, all right, whatever.
Well, the horizontal should.
Okay, well, with this structure, in this case, too hard to see that O3 has a either an H2 cross R, like we had structure here for the surface cross R, or a twisted version of this SL2R tilde structure. So by that I mean that, in particular, if I take a meridian going around here, it corresponds to a rotation of order 2. Something around here is a rotation of whatever order, well, with cone angle there of 2 pi over alpha I. Okay. So it has this sort of structure, and so in particular, there exists. Well, in fact, it comes from the fibering. There exists a projection. Okay. There exists a projection from, well, this is the underlying manifold. It's usually put absolute value here. So this is just from the manifold here down onto P2, and again with the fibers coming from the Seifert fibering with a transverse hyperbolic structure. So it's natural to ask. So in particular, if I took the complement of the whole singular locus, or there's actually a hyperbolic structure on this thing of a suitable sort. And we can ask in the similar way whether we can get this. We want to think of this as a collapsed three-dimensional hyperbolic structure. It's actually like a dimensional hyperbolic structure when I push down here. Whether there are, in fact, hyperbolic structures with singularities along the singular locus here that collapse as the angles go towards the orbifold angles. Okay. So in a very pretty paper by Joan Porty, proved the following, that there exists, again, hyperbolic cone structures, which again, the local models around the edges are the same as they were over here, and you can kind of guess what they would look like at the vertices. Hyperbolic cone structures on, I guess, I put O3 absolute value with cone angles just slightly less than pi, which is which would be the cone angles on where there are the 2's there, say epsilon here on the vertical fibers, horizontal fibers, horizontal singularities. On the horizontal singularities, and then the cone angles equal 2 pi over alpha I. They're fixed on the vertical. So the idea is we can find a bunch of singular hyperbolic structures where the cone angles around these red pieces stay fixed at the sort of orbifold angles. If I actually had angle pi here, then it flattens out, but when the angles are less than pi, in fact, it doesn't. It's actually a robust three-dimensional thing here. And in particular, as you guess, the whole point here is that as epsilon goes to 0, this flattens to hyperbolic structure on P2. But as long as this is something where, again, we're fixing these angles here, but there's a whole Teichmuller space of things here, right? There's actually, as long as this isn't a triangle, then there's actually a whole parameter family of these elements here. And so we can, again, ask the same question, which structure? On P2. And again, what Porty proved is that there's a unique hyperbolic structure on P2, again with this in the sense of this sort of reflection group here, that minimizes the lengths of the perimeter here. Okay, so the answer is that it is a unique structure minimizing length of perimeter. I'm sorry?
Does this still hold if the polygon is a square with all interior angles pi over 2?
Well, that's not hyperbolic, right?
So you're only allowing
Yeah.
the condition of the polygon?
Hyperbolic.
Oh, okay.
Right, yeah. But it would hold for a rectangle with other angles if it's hyperbolic, yeah, right. Although I guess there's not orbifold ones. Anyway, yeah. So again, we see, and again, the fact that there's a unique minimizer is sort of convexity properties of the length function, although Joan actually had a independent and more direct proof that actually shows that the one that minimizes is the unique one that has an inscribed circle, hyperbolic circle in there. So that's actually a really nice little argument. So it's better than using all the apparatus of the sort of convexity properties. Okay, number 4.
In your first example, you mentioned this business with going through PGL4. But
Right. Yeah. So since I'm short on time, there's he actually controls the collapse in such a way that you can apply Danziger stuff and actually go through, have it conjugate to an HP structure and actually go into an ADS structure. So that actually, I mean, that's just a sort of throwaway line in there, but it fits in with Danziger's.
And it goes to SO22. I mean,
Yeah, yeah. But the main thing is, in order to do that, you need to control the collapse here. No, in fact, that's the point. Actually, that was the big surprise. That was, for many years, what we all thought from Thurston's work and from the notes where he did certain collapse like that, that the thing in the middle should be this geometric structure that they had. But part of the big surprise in Jeff's original work is that these HP structures. No, the HP is the middle. It's the analog of the Euclidean. The other ADS is on the other side. Yeah, right. Yeah, so that was a sort of major shock to all of us, in fact. Yeah. Okay, so the final example. I have to zip through this a little more than I'd hoped, but at any rate. So this involves another geometry I haven't talked about, Sol geometry. SOL geometry. So for solvable. So the model space here, let's see, how am I going to do this? So the model space for this that everything locally is modeled on is just equal to R3 with the usual coordinates, but metric e to the minus 2z dx squared plus e to the 2z dy squared plus dz squared. And so, in particular, the isometries at least the identity component here of Sol geometry, they correspond to things of two types. Oh, so let me draw a picture over here. So what does this look like? We have these planes. If you fix z, you notice that you have just a Euclidean metric on any horizontal plane here. But as I go up, say in the z direction, I'm not sure why this is red, but it's going to be red. And then, so this is along the x-axis, and then there are similar pictures going. In the y direction here. So if I take, and then there are these foliations by x direction and y direction going here. I have a Euclidean metric here scaled in a certain way at any given level. But as I go up, something here an isometry, it's going to take something here and actually stretch it out to something bigger, to your Euclidean eye, because it has to be the same length. And because of this, it's being damped more. So an isometry here, so what I was going to say is, in particular, a vertical translation. Again, with where I stretch in the x direction and squeeze in the y direction. In this fashion here. And then also just any xy translation, xy and xy, just Euclidean translation. So I guess two things about this in particular. Well, we've seen this. This geometry was almost built for the closed manifolds that have this structure are of the form T2 cross I divided out by x0 is equivalent to psi x1, where psi T2 here is an Anosov map. Anosov map here. This has a property on, if you're thinking of it acting as a linear map on R2, it has directions of stretching and ones of squeezing that descend to foliations on this with exactly that. So the picture here would be that you would have the foliation, expanding foliation, and the contracting foliation along the axes, and then the lattice for the torus would be off at some angle there. And as you go up, you do the stretch squeeze. So these all have sol structures. And in fact, these are up to index, maybe even to any finite index, are the only closed three manifolds that have this structure. On the other hand, I want to point out that if you look at, say, so we have these horizontal things here. They're not totally geodesic. They are minimal. There's a minimal foliation. But if I look at the vertical things I've drawn here, this and this, these are actually copies of H2. So if you think about forget about this and this, by taking log of z, you end up with just the hyperbolic, the upper half space model of H2. The difference, however, is that horocycles get bigger, I guess, this way in the x direction and smaller in this direction in the y direction. Okay. So there are these copies of H2 here. So in particular, there exists projection onto, well, in fact, both H2s, and we get a transverse hyperbolic structure. And the image of the isometries that I get here when I project to H2 is actually non-discrete, but a metabelian representation in SL2R. Okay. On the other hand, if I remove a point, say an invariant point like the origin here, so if I take T2 minus a point cross I, again divided out with this here, this has a complete hyperbolic structure. And so, back actually in Thurston's notes, in the case, so this actually, the figure 8 knot is an example of this. And, but instead of the singularities being along the meridian, it's actually along the longitude. Okay. And so in particular, what was clear from Thurston's notes is you could actually go from this complete structure through cone structures all the way to cone angle 2 pi and collapse onto the sol structure. Okay. So that was done for the figure 8 knot, but then Hüsner, Porti, and I'm going to forget her name, Suarez. Showed that there exists cone structures on T2 cross I with this equivalence, again along this point across S1 with cone angle cone angle alpha, which runs from the cusp version, where it's 0, all the way down to 2 pi, and then it collapses to the H2 structure, or either one of them, either corresponding to the sol structure. And again, Jeff Danziger showed, in fact, there's a transition in this case. Okay, so the one thing I at least want to mention is sort of more, so this is a little bit of old news, but somewhat less old news. What about the case?
And the transitions through like Halfpipe Geometry?
Yeah, same. Yeah. What about higher genus? So in this case, right, we have this map from F2 to itself, where G is greater or equal to 2. And again, we have invariant measured foliations, only with singularities. So there's like something like this, 2 transverse measured foliations. Picture like this. So away from the singularity, it looks just like the picture for the torus, in which invariant foliations, F plus or minus, that are stretched and squeezed. On the other hand, if I take F2 cross I with this, take the closed manifold corresponding to this, this has hyperbolic structure, a smooth hyperbolic structure. So this is one of the big parts of Thurston's original work on the geometrization, has hyperbolic structure here. So now you can ask, is it possible to take out the singularities coming from the suspension of the suspension of the singular locus here, and whether it's possible to take a bunch of singular hyperbolic structures, starting at the non-singular one where the cone angles are 2 pi, increasing the cone angle until it hits, so in this case, I should have said here, this has, so using this structure here, this has singular sol structure. Again, where the singularities come from along from the suspension of the singular points here. Okay.
So you remove them and start with cone angle 0 and triangle.
Well, I'm actually starting with cone angle 2 pi is right. Actually, what if I want to recreate the closed hyperbolic structure?
And then you want to go.
Well, actually, I want to go back the other way. I want to regenerate. I want to start with this structure, singular sol structure, and push and decrease the cone angle to get to the closed structure there, right? So can we, so again so this has cone angle. Cone angles of the form k pi, where k is equal to the number of prongs.
But is it?
Let me just finish, okay? So I'm already over time. So the question here is, can we decrease cone angles back to 2 pi to get the smooth structure, smooth hyperbolic. Okay, again, decrease the cone angles going through hyperbolic structures and so on. So this was has been an open question for, well, since I was a student, so we won't do the math. But, and there was really no progress on this at all, but let me just mention that, so we still don't know this even in special cases, but Kenji Kozai proved that under certain circumstances that if the, well, I won't say what they are under special circumstances, conditions, you at least can get started, started, meaning that you can find cone structures with cone angles strictly less than the ones that we have here, and that actually degenerate under here. So in particular, one of the conditions that are needed here is that this closed 3 manifold that we get here actually has the homology, cohomology group as small as possible, just equal to Z, or R Betti number 1. In the case of higher Betti number, it's something that we're working on now, but that's much harder because there are an infinite number of vibrations. Sorry for going over.